Hi everyone, my name is Sognik, and for this final project, I will be presenting the paper Accelerated Mirror Descent in Continuous and Discrete Time. It was a paper from UC Berkeley, and this paper is particularly relevant to our recent lectures because it bridges the gap between standard gradient methods that we learned and some of the more advanced techniques that we covered in the final weeks. So just to get into the motivation, why is this paper important? So throughout the quarter, we focused on gradient descent and projection methods that converge at a rate of O of 1 over K. So while this is robust, this can be slow for large scale problems. So this paper introduces a framework that achieves a quadratically faster rate of O of 1 over K squared. And what makes this paper unique is how they derive it. Instead of just giving us complicated algebraic update rules, the authors model the optimization process as a physical system, specifically an ordinary differential equation. This gives us a physics-based intuition for why momentum works. And furthermore, it combines acceleration with mirror descent, allowing us to handle complex non-Euclidean constraints very efficiently. So we can, go ahead and look at the problem setup here. We are solving the standard constrained convex optimization problem, which is minimizing a convex function f of x over a closed convex set x. We assume the function is smooth, meaning the gradient is Lipschitz continuous. However, the key distinction here is the geometry of the constraint set x. In class, we often looked at Euclidean constraints like a ball or a box, but this paper focuses on cases where the geometry may be non-Euclidean. So a classic example is the simplex, where variables represent probabilities that sum to one. Standard Euclidean projection onto a simplex is computationally expensive and geometrically very unnatural. So this motivates us to use mirror descent, which adapts the distance metric to fit the geometry of the problem. So getting into the core algorithm, which the authors derived by discretizing the ordinary differential equation. It couples two sequences, a primal variable x and a dual variable z. So there are three key steps. First, you'll do a dual update. So first we update the dual variable z. The step access our momentum. It accumulates gradients over time rather than just reacting to the current slope. And then we have the mirror step. This is the most critical part. Instead of just performing a standard projection, we solve a minimization problem using a generalized distance, denoted here as d sub phi. This allows us to take larger steps that respect the constraint geometry. And then we have our primal update, where we finally compute the new position x as a weighted average of this mirror step and our previous position. So yeah, just to get into some assumptions, guarantees that we made. So what guarantees does this method provide? So the authors prove that if the function is convex and smooth, and we choose our parameters correctly, the algorithm is guaranteed to converge at a rate of O of 1 over k squared. And then, so this is the acceleration we're looking for. We're trying to go from O of 1 over k to something a little bit quicker. O of 1 over k squared is quadratically quicker. And then, however, there's one catch. The system models a damped harmonic oscillator, like a spring with friction. So the momentum can cause the trajectory to oscillate around the optimum. This is a trade-off. We get to the neighborhood of the solution much faster, but we might spiral around it before settling, unlike the, monotonic descent of standard methods. And then just connecting this back to, what we covered in the course. In week 6, we talked about the gradient projection method. In class, we learned that the projection step is found by minimizing the Euclidean distance, essentially finding the closest feasible point in a straight line. We solve these, using KKT conditions. But this paper is, generalizing that exact concept. The mirror step is simply a projection where we replace the Euclidean norm with a generalized distance function. That's called the Bregman divergence. And just like in class, the authors use KKT stationary conditions to solve these subproblems efficiently. So mirror descent is really just projected gradient descent adapted for curved geometry. And then, if we start to get into the experimental results, if you look at this experiment, the size was n equals 100. The figure shows the error on a log scale for a problem constrained to the simplex. The black line is the standard mirror descent, which converges at O of 1 over k. You can see that the slope is shallow, and the colored lines are the accelerated methods, O of 1 over k squared. You can clearly see a much steeper slope, proving they are significantly faster. However, look at the ripples. However, if you looked at the ripples in the green line, these ripples visually confirm the oscillatory behavior predicted by the ODE theory I mentioned earlier. And the method moves fast, but it carries momentum that causes it to wave back and forth as it converges. And yeah, just to sum this up, I do want to acknowledge that I did utilize artificial intelligence to help me. But part of the core policy, I will acknowledge that I used Gemini to assist with this project. I used it to format these slides in LaTeX and to also outline the script structure, just to make sure that I hit all the requirements. But all the math explanations and derivations are accurate and done by myself. So.